Welcome to the 2016 NASA Ames Summer Series. This year's series consists of 18 lectures from various experts in different areas. Please join us for the entire series, not only for the ones that seem interesting to you. You never know what you may discover. Radiation tolerance of electronics is critical for risk reduction if we're going to go explore beyond low Earth orbit. It is critical for the vehicles that we will use and utilize as we go across exploring other planets. Vacuum electronics, when you think of that term, you think back in history to tubes and the old radio systems that existed. But they also hold the potential to have radiation immunity for electronics. Today's seminar, entitled Vacuum Electronics in a Nanometer Era, will be given by Dr. Jin-Woo Han. He received a BS in Information and Communication Engineering from Inha University in Korea, and an MS in Electronic Engineering in 2006, and a PhD in Electrical Engineering from Korea Advanced Institute of Science and Technology in 2010. Then he came and joined Ames Research Center as a postdoc, and now he's a research scientist with USRA at NASA Ames. He has many accomplishments in his early part of his career so far, including the recent 2016 Presidential Early Career Award for Scientists and Engineers. Please join me in welcoming Dr. Jin-Woo Han.
Thank you, Jacob, for having me this opportunity to present my project and work. So today's my talk is about how the vacuum electronics play in a NASA mission, how it advanced, how it revolutionized the NASA mission. So Jacob introduced very well, but I want to repeat it again. In the space, there is an abundance of space radiation, including some X-ray, gamma ray, proton, neutron, whatever you call it. We have to make a space system that is highly tolerable against to the space radiation. Not only for space radiation, there's a high temperature found in the outer planet. So in case of Venus, the Venus surface temperature can exceed as high as 500 degrees Celsius, which means that their qualification has been treated differently within Earth's application, because no electronics we tested on the Earth's application does not exceed about 200 degrees Celsius. So we have to pay different attention for their reliability aspect. Not only for Venus, for example, if we do some re-entry and the descent and landing application, the surface temperature of the shuttle can exceed about 1,000 degrees Celsius, while we want to monitor what is happening during the re-entry period. So for that perspective, we also deal with some electronics that can work as high as 1,000 degrees Celsius. So here is an example of the failure or the error found in the NASA mission across the different spacecraft. Upon the space radiation, there is a humongous different type of errors were found in our previous mission, which includes some bit error, something like some power failure, some upset of the electronics. So this is just an example. So it means that we need to find a way how to deal with, how to minimize the risk upon the space radiation. So here's my contents of my today's talk. Then I will go further. So what I'm trying to talk today is very relevant to the fundamental building block of electronics. This is an example how we want to explain the cause of the failure in space electronics. There's a curiosity. This is our system, the rover. But every system contains printed circuit board, which contains the population of electronic device, which is called IC, integrated circuit. And then within the integrated circuit, there is a fundamental building block, which is called a transistor. And then billions of transistors are combined, and they're placed and routed as we build up a Lego. It functions as a single functioning chip. So the failure mechanism of the electronics is very relevant to the failure mechanism found within a transistor. As you see in the left, the lower figures. And here is a schematic view. And then I will explain a glossary of the transistor. So transistor is basically made out of the semiconductor materials. And then we place which is called source and drain. And the resistance across the source and drain is controlled by the third terminal, which is called the gate. And between the gate and the channel, there is an insulator that is designed to deliver electrostatic field, but preventing the electric current leakage through the gates. And then around the single transistor, the transistor is isolated by the insulator. So this is the fundamental structure of the device. And then what I want to focus is all the material is consisting of three basic blocks, which is insulator and metal and semiconductor. And then what is happening in the material is this. So this is an example of atoms, which becomes a fundamental species consisting every element of the material. So when high energetic particles are hitting the atoms, and then the momentum transfer from the energetic radiation into the atoms, it actually knocks off the outer bounded electrode, then make the atoms ion, and it leaves free electrons. And these free electrons become freely moving across the electric field. So this is how it causes failure in semiconductor system. So as I explained, there is three materials. One is metal, conductor, and semiconductor, and insulator. The material guys of the device physics guy use a term called energy gap. So I don't want to go in detail, but in conductor, there's already a humongous amount of free electrons there. So the energetic space particles hit the conductor. It may create extra electrons, but it doesn't do much because there's already free electrons there. But in semiconductor, their density of free electrons can be modulated upon the voltage applied across it. So it can be either insulating property or the conducting property, depending on what voltage we are applying it. But when space radiation penetrates through the semiconductor, it creates a free electrons. Then, in case the semiconductor is supposed to be an insulator, but the ionized electron due to space radiation, it acts as the semiconductor is a metal conductor. So it causes a malfunction of the transistor. So this is one aspect. And then in insulator, even though the band gap of insulator is too wide, so even though we apply high potential, it never turns into the conducting properties. But when the radiation hits the insulator, it creates ionization, but this ionized electrons is not like a free carriers, but it's localized and it acts as a defect within the insulator. So the basic difference between semiconductor and insulator is that in semiconductor, it is like a spontaneous and it's momentarily. So it means that as time goes by, the free electrons recombine back and then it return back into original states. So it's like a soft adder. But in the insulator, once it ionizes it and then it becomes localized and fixed it, so it's cumulative, and it ages as time goes by. So we can discriminate the soft error and hard error, which is aging, what we call it as a total ionizing dose, TID in short. So there are 3 types of error. Some soft error, instantaneous, which is relevant to semiconductor, and then second one is cumulative, which is aging, relevant to the oxide, which has a higher band gap. So this is a schematic view. When the energetic particles are penetrating through the semiconductor region, and then the heavy ion has a higher mass, so it penetrates all the way through from the surface of the silicon into the bottom of the bottom surface of the silicon, and then it creates the charge funnel. But for the proton, such as a relatively lower mass, and then it creates just a single pair or second pairs as extra. So what happened in reality is when we build a circuit, we build a circuit by using 2 different polarity of a transistor. One is called an N-type transistor, and the other called P-type transistor. But when the N-type transistor and P-type transistor are placed side by side to result in a certain function, this is called like an inverter function. This is a very basic building block of the logic circuit. Then in the bottom side, the bulk region of the device, it creates some parasitic transistor path, which is supposed to be always off. But this parasitic transistor, which is denoted in line figure in the view graph, it is initiated once it is triggered by the radiation ionization. So the device is supposed to be always off. The parasitic feedback loop is supposed to be always off, but when space radiation initializes the creation of electron-hole pairs, then it initiates the feedback loop, and it becomes always on state. So this is one of the causes of soft error. And then the other one is what I call a cumulative errors. And then this cumulative error is related to the insulating region around the channel. And then, as I explained, this is localized and fixed, and is cumulative. So these fixed charges act as a pseudo gate formed in the sidewall of the channel. So the role of the insulating region is just isolate the one device to adjust the device. But as time goes by, as it contains the localized charges, these charges form a parasitic transistor path on its side wall of the channel. So it weakly turns on the device. And the other insulator we found in transistor is gate insulating oxide, which is on the right and top portion. Even though the thickness is very thin, that it is also insulator, so it contains fixed charges. These fixed charges are used to degrade the drive current of the transistor and increase the leakage current of the transistor. So this shift device parameter, like some drive current and offset leakage current, threshold voltage, and then slope of the transistor IV curve. So how we countermeasure this radiation effects is this. This is too many approaches, but to make it short, the most straightforward way to mitigate the space radiation is shielding the entire electrons within a very thick box of the metal. Then the metal shield and absorb the space radiation. For that way, the space radiation doesn't reach into the device. But as of NASA mission, we are all focused on the mass of the payload, because every pound we want to lift onto the lowers of it, it costs the weight translate into the cost, right? Then if we want to save this cost. So I was thinking that what if we make a device which is intrinsically resistance, immune against the space radiation. So that was my starting point. So this is a brief history how the space electron society have evolved the device structure. So figure on the very left is very early stage device structures, which has become actually a standard process. But as you see, the sidewall of the transistor is interfacing with the materials that cause a parasitic leakage path of the transistor. So the people were thinking that we need to minimize the contacting area between the semiconductor channel and insulating region. So the second generation is making a device on top of insulating region. By that way, we can minimize the overlap area between semiconductor and insulator. But still, the backside of the channel is interfacing the material. So as long as there's a insulating material and semiconductor material contacting each other, we are intrinsically not free from localized charge effect. So the next generation is, what if we fully surround, making a silicon channel suspended into the air and then fully surrounded by the gate conductor. By that way, we can minimize the impact of isolation. But still, even though the volume and thickness is very thin in the gate oxide, but as long as the semiconductor is interfacing with the gate oxide, it's not completely free from the radiation effect. So what I suggested here is, what if we remove the gate oxide, which is solid, into the vacuum? Because the vacuum is also insulator, right? So vacuum can work as an insulator. Maybe it's not as efficient as silicon dioxide, but it's still insulator. So if the vacuum is surrounding the silicon nanowire channel, then there's no material contacting to the channel. It's fully suspended, floating, right? So there's no material that being damaged, being degraded upon the space radiation. That was my first generation of idea. So this is brief history. So in order to prevent, the figure on the left is the parasitic transistor path formed in the bulk region of the silicon. Then in order to remove that region, so we used to make a device on top of some insulating region. By that way, this N-type transistor and P-type transistor are electrically decoupled. So we don't have to worry about the parasitic, positive feedback loop. But even in single transistor, later on, the scientists discovered that even there is no, N-type and P-type transistor within only a single transistor, it still can be offset upon the radiation, because this body area, which channel area, is electrically floating, right? So when the space radiation generate electron-hole pairs within the silicon channel, the excess amount of generated charges, there's no way to dissipate. So it is accumulated only inside of the channel. So these generated charges work as another source of the input current. So this input current turn the device on. So even not only for the N-type and P-type transistor, but only even within the single transistor that can cause error. So second trial. So if you think how this generated density of generated charges are formed, then you can easily imagine that the charge density created by the space radiation should be proportional to the volume of the channel itself. So the larger volume means the larger the ionization. So this is the history how we have evolved the device structure. So basic idea is to minimize the volume of the channel. So we used to build a relatively thick channel, but to minimize the volume, the radiation sensitive volume, then we reduced the thickness, and then we went to the silicon nanowire. But ultimately, what if we use nothing? So if we follow this trend, so we know the vector, how the trend goes up, then we can like jump into the all the way down below. So it can be a 0 in volume, right? So which means the vacuum. So this is my second strategy to mitigate the error. So these are two structures. First one is like a near-term future. So using silicon nanowire transistor surrounded by the surrounded by the vacuum edge gate dielectric. And the ultimate goal is to make a fully vacuum as a charge carrying material as well as gate insulating material. So this is a device I made. So there is a source and drain, and the gate is fully surrounding the channel, but it's not seen because the gate covers the channel region. And then there's the vacuum gap between the channel and the gate. So I made a device. So the plot on the right-hand side is a very representative curve of the current across the source and drain controlled by the third terminal, which is a gate. So it showed very good characteristics, but one counter offense I can being asked is that, so we want to have the good control of the gate toward the channel. So we want to have good electrostatic control from the gate to the channel. So in order to have a good electrostatic control, we want to have a high dielectric constant of insulating material. But as you can imagine, the vacuum has the lowest dielectric constant found in the Earth, which has a 1. But for example, the silicon dioxide, which becomes a very widely used material, which has around 4 dielectric constant, but the vacuum has very poor dielectric properties. So there is parameters called scaling length, which signifies how this device can control that on and off. So if you look at this characteristic length, the model, then the electrostatic control is not only function of the dielectric constant itself, but there's some physical term there. So what this model tells us is this: if we make a very thinner and thinner and thinner the gap, it increases the better and better electrostatic control. So we can overcome this poor dielectric constant. So here it comes to the space radiation test. Of course, we didn't shoot it to the space, but we can emulate the space radiation by using some radiation irradiator in Earth. So I tested the gamma ray on the gate around nanowire transistor. And then, as you can imagine, as there is no material that being damaged by the radiation, the high radiation does not shift any device characteristics here. So let me move into the vacuum channel transistor. So some of you guys seen that the vacuum tube. So actually the vacuum tube sparked the electronics era back in 1940s, right? So we may have seen that some glowing the vacuum tube for very high fidelity speaker amplifier in audio system. So still there is some use for the vacuum tube, but most of our modern electronics is relying on solid state device. But if you look at the history, why the vacuum tube went a dinosaur way, but that the solid state device become a workhorse for modern electronics is not because silicon is better than the vacuum as a charge carrying material, but there's another aspect that took for the transistor took the vacuum tube's role. So intrinsically speaking, the vacuum is a better charge carrying material than silicon because there's nothing there. So in case of silicon, the carriers are scattered or colliding with the silicon materials. So it actually degrades the drive current capability. But in vacuum, there's nothing. So theoretically speaking, we can get the speed of light for the electron transport. So in terms of performance, the vacuum tube is still better than silicon. But there was a huge drawback of the vacuum tube. So one of the drawback of vacuum tube is this. So even though we use the term vacuum, but there's no vacuum. No, there's no ideal vacuum we can make it on Earth. So in the vacuum tube envelope, the one issue was packaging, but the second issue is that there's some residual gas found in the vacuum tube. So even though the statistics that the probability that electrons can collide with the residual gas is relatively low, but as soon as they accidentally, hitting the residual gas, actually these electrons can ionize the gas into the ions and the electrons. And then as the vacuum tube is applied certain voltages, then this ion, which has like a relatively very heavy, bombard into one of the electrode. So it degrades the material property, the mechanical structural property of the electrode. So probably you can imagine that you may see from the Google image that some ENIAC computer, the engineers actually replaced the vacuum tube from one to another, right? Because the one major issue for the vacuum tube was the lifetime of the vacuum tube was relatively poor. So that was one drawback. So I was thinking this, so it's basically impossible to 100% avoid the collision between the electron and residual gases. This is periodic table showing the number shown on the periodic table is the ionization potential, which means how high voltage or potential is required to ionize this atom into ions and electrons. So if you look at all these numbers, the lowest number we can find out is about 5. So it means that in order to ionize this atom into the atom into ions, we require higher than the 5 electron volt as energy. So what if we make a vacuum tube that operate under 5 volt, which is maybe some battery relevant voltages? Then we can let them collide with the residual gas, but this collision is not, the energy for the collision is not as high to create ionization. So our first target is to make a vacuum tube that operates less than 5 volt. That was first criteria. And then second one is this. This figure shows the air molecule. And then figure on the left is just, for example, for the sake of simplicity, let's say this is a atmospheric pressure on the left. The air-to-air distance is quite close. But for example, the figure on the right is something like 1 millibar in pressure. Then the distance between the two air molecules are very far. So this table is a mean free path for different pressure. So in our ambient pressure, which is 1 atm, the mean free path of the air molecule in the air we are breathing in is about 70 nanometer. So it means that we feel abundance of airs here, but if we zoom in and magnify all the way up to beyond 100 nanometer scale, then there's a chance that we never see the airs. So we can call it as the quasi-vacuum, right? So there's two strategies. If we make a device extremely small, there's the chance for the electrons collide with the residual air is decreased. And even though there's a collision there, if we make a device operating below the battery operating voltage, such as 5 volt, we can just let them collide. Then there's another the weakness found in the conventional vacuum tube. So you may see that the vacuum tube is glowing, then it looks really beautiful, right? But actually, that glowing is not necessary for their intrinsic operation, but it is required for driving extra current. For example, the vacuum tube, you see that you can actually see by using our naked eye. So it's a human scale. Its scale is about a millimeter scale. For that millimeter scale, in order to extract the electron out of emitter electrodes, we have to apply 1,000 volt, but which is not very readily available for any applications, right? So in order to lower the operation voltage in the conventional vacuum tube, what happens is we heating up of emitter electrodes. By that way, the heating can inject extra electrons. By that way, you can reduce the operational voltage. But still, the operational voltage of conventional vacuum tube is kind of 100 volt. So the energy required to heat up the cathode, which is an emitter electrode, consume more energy than is intrinsically required for the operation. So it's another drawback. So if you understand how these electrons can emit from some solid material into air, in our classical understanding, it's impossible for the electrons escaping from the confined matter into the air. But in modern physics, we now understand that these electrons can be escaped from out of the confined state, which is called tunneling, quantum effective tunneling, quantum tunneling. So it means that the quantum tunneling, in order to increase the tunneling, actually is very relevant to the electric field at the surface of electrodes. So if we can make a device which electrode has an extremely high electric field, then without actually hitting the device, it actually the emitter can emit sufficient amount of electrons for the required target. So this is a quantum tunneling model. And then if you look at this model, there's two factors that we can engineer. The first one is electric field at the cathode, and second parameters we can engineer is work function of the cathode itself. So one is kind of structural matter, and second one is material matter. So it means that by engineering the structure of the device and the material of the device, we can make a vacuum tube free from heating element. And then electric field can be modeled, the localized field at the surface of the emitter can be modeled this kind of equation. But it's very intuitive that the sharper electrode, the higher the electric field at the tip of the material. So here, and then there's the first one is we want to make a device, the emitter tip as sharp as possible to intensify the localized electric field at the surface, at the tip. The second one is in order to increase the gate controlling efficiency. So this is a simulation result of the electric field for the gating structure. The first one is just planar gating. The gate is placed on just top of the emitter tip. And if we place the gate top and bottom, then it not double, but it efficiently increase the localized field, and then triple, increase again, and then quadruple, increase further again. But you can imagine that the ultimate gating structures we can implement in three-dimensional world is actually surrounding the tip, right? Then there's no further way to increase the gating other than surrounding gate. So I was thinking that we had to make a very sharp tip, and we wanted to make the gate which is fully surrounding the surface of the gate. Then this is relatively, too technical. But the message I want to deliver in this slide is this: instead of bulky three-dimensional materials, but if we make a emitter electrode, which is kind of 1D fashion, one-dimensional fashion, the 1D means it's kind of like a whisker type of thing, then the transmission probability becomes better than its intrinsic material property. So it means we can further engineer the tunneling probability by having the nanowire type of electrode. So here it comes to the fabricated device structure. So this is quite similar to the device I showed previous slide, but one difference is that actually there's empty gap, empty cavity within there's the gate. There's a small hole, but there's nothing there. It's hard to see because it's fully veiled by the gate. And then there's a emitter, which is really sharp, and there's a collector, which collect the emitted electron, but on the other side. And again, it showed the fairly good the electron current controllability. And the question I've been often asked by others is how we create the cavity inside of the gate. This is a fabrication flow. So in order to, as I explained previously, our target is to create the empty gap less than mean free path of the air molecule in our atmospheric pressure, which was around 70 nanometers. So I was targeting to make a device less than the vacuum gap less than 15 nanometer. But for the sake of understanding, in some lab scale, actually the critical dimension we can create at a given fabrication facility is called a critical dimension. But the critical dimension in just regular fab in Stanford and UC Berkeley, they offer around like a 300 nanometer as a minimum feature size. But for Intel, as of now, Intel can fabricate the device less than 17, 14 nanometer in the scale. So there's a huge gap between industry and academia and research institute. But my target was beyond of critical dimension that you can buy, you can rent their equipment. So this is fabrication flow, how we can get the empty cavity less than 50 nanometer is this. So first, we make a silicon, suspended silicon, shown in the figure A. The figure B is we expose entire silicon nanowire, the suspended silicon nanowire, into some oxidation process, which convert the silicon into silicon dioxide. Then I expose it until the center portion of the silicon nanowire becomes fully oxidized. Then this fully oxidized silicon dioxide, we're gonna use it as a sacrificial layer that's gonna be removed, selectively removed later on. So traditionally, the critical feature size is determined by the photolithography. But this one, the critical dimension is nothing to do with the photolithography, but it's controlled by the oxidation process. So in the figure C, we deposit some gate material and then pattern the gate. Then the sidewall of sacrificial oxide is exposed. Then you can just etch out the silicon dioxide. Selectively, then we can make a vacuum gap only within the location there. So this is probably final last slide. So also we tested for the space qualification. So we tested under proton and gamma ray, and as you expected, there's no materials that being disturbed by any kind of space radiation. There's no the device parameters changes found. So here's the N. So let me wrap up this seminar by saying this technology shows great promise for making radiation tolerance integral to existing electronic architecture and enabling future deep space science mission. Thank you.
So we have time for some questions. If you have a question, please raise your hand, wait for the microphone, and ask one question.
Hi. So I have a question about the practical matter. I suppose on Earth, it's maybe it's a bit of a disadvantage or a challenge to have to maintain the vacuum in your device. But on the other hand, in space, is it sufficient to just expose your devices to space vacuum? Is that a good enough vacuum?
So my answer is this. We have our iPhone, right? In our iPhone, probably you may have heard about the technology called the MEMS, the mechanical electromechanical systems, the micro electromechanical systems. In our cell phone, in our iPhone, we have some gyroscope, accelerometer, something like that, which is implemented by the MEMS. But for the MEMS technology, they are relying on some freely moving part within the chip itself. So actually, I was speaking like that. The vacuum packaging technology is already available. So it's already mature technology in the market. So whether or not we're going to use it in the Earth for the space, the vacuum packaging, at the moment we're going to implement in the reality, we're going to package this device into the real chip. Then we have a vacuum packaging technology ready there.
Jin-Woo, I have a question back here. So there's technology that's gone into deep space, like the Voyager, for example, that was launched in the early 1970s, and continues to send information back to us. I mean, we have data from instrumentation that's been in space a long time, that's been exposed, that's old technology, ancient technology by current standards, right? How have those technologies failed, or was it just redundancy that allowed them to survive so long? I mean, why have we been so successful?
So there is a silly way to overcome the space radiation effect. The most easy one, most straightforward one, then, which is actually implemented one in NASA, is actually shielding the entire electronic system by using thick metal, which I explained is actually redundancy, and it causes a payload, and it's a weight penalty. That's the first one. The second approach is when we design a circuit, there is a expected performance we can bring out of this design. But for the space mission, actually we use less performance than it actually gives us. By that way, we can have a larger tolerance against the radiation. So we are giving up a performance that you can actually attain from the design. The third one is we usually, I don't know, not every mission, but some missions for the mission critical components, we put like two or three exactly the same chips, and then they're gonna use as the one by one. So by that way, you can extend the lifetime. But again, this is also expensive and redundant. But my technology is intrinsically free from the space radiation damage.
A follow-on question, in biological systems, the solution is to do repair. Have you considered systems that would be somehow self-repairing?
It's a really good question. And then actually, we submit some proposal to mimic the human immune system in electronics. So what do you say? The self-immune electronic system, we propose some proposal. So we are waiting that. So yeah, we have.
So thank you very much. Please join me in thanking Dr. Han again for an excellent talk. Thank you.